Hello and welcome to today's lesson on sound detection, which is formed in the waves topic of GCSE separate science physics. So in today's lesson we're going to look at how we can use sound to detect objects. So if we've been successful and we've learned in today's lesson, we can understand how different sound waves can be used to determine object properties, calculate the distance an object is away via sound detection, and consider the applications of sound detection, which falls into the following part of the GCSE Separate Science Specification 4.6.1.5, Waves for Detection and Exploration, which is a separate science or physics only content. So ultrasound imaging has been used in the natural world for millions of years. Bats and dolphins echolocate by emitting ultrasound and listening for it off its reflection off nearby objects. Many species of bat use this to locate their prey, but ultrasound was also first used for a medical purpose in the United States in the late 1940s. Today, its most well-known technique is used to view fetuses during pregnancy, but it has other medical uses as well. Now, ultrasound tends to be used in medicine because it's harmless, it's non-ionizing, it produces real-time images of soft tissues of the body. However, its main drawback is that it produces a low resolution image. Now, to measure the speed of sound, we can use a method that many animals use to determine the distance of objects from them, and humans use this subconsciously too. So we can measure the speed of sound by considering the reflection of sound waves off objects. Now, the detection of objects using the reflection of sound waves is called sonar, sound navigation and ranging. Now, radar works on the same principle as sonar, except they don't use sound waves for the reflection, they use radio waves. So the speed of sound can be measured by reflection. So in the process, a sound wave is emitted. It is then the sound wave will travel through the air, but this process is not instantaneous for any wave, as all waves travel at a finite speed. The sound wave will then hit another object and reflect. However, remember, it's only a partial reflection because some of the sound wave will be absorbed by the object and some of the sound wave will transmit through the object. The sound wave will then travel back to the emitter and be detected. We can then work out the speed as speed equals distance travelled over time taken. Now just remember, when we're working out the distance travelled by the sound wave, it's twice the distance between the object and the emitter, because the wave has gone there and it's gone back. Now in this method, any material can be used for sound to travel through, but in this case we're just using air. Now, like mentioned before, the scientific name for this method is called echolocation, locating sound waves via reflection or echoes. Now this method assumes that the sound wave of the wave doesn't change throughout the investigation, the medium it is travelling through has a constant density, and that the wave travels in a straight line. Now, the intensity of the sound wave decreases in this investigation as the object will absorb an amount of the wave when it reflects against it, and some of the wave will actually transmit through the object. Now, in the example of ultrasound, we call the emitter a transducer. Now, in reality, most of the ultrasound wave passes through an object, a little part of the ultrasound wave reflects, and a very, very small amount of the ultrasound is absorbed by the object. So what will happen is the incident wave, well, most of it will travel through the object, a small amount will be absorbed by the object, and a proportion of it will be reflected back to the transducer. Now, for medical purposes, the object tends to be a tissue, like a blood vessel or the skin or a muscle tissue. Now, when there are multiple tissues, there are going to be multiple reflections. But remember, you can only measure multiple reflections if not all of the wave is reflected back. There's only partial reflection of the wave, and there is some transmission of a wave through a tissue. Now, the time it takes for the sound wave to return tells you the distance the tissue is away from the transducer. So it tells you the depth of the tissue. Now, the intensity of the reflected wave tells you the type of material the tissue is made from. The denser the material, the more of the sound wave that is reflected. Now, we can use this in medical scanning, and we can also use this in industrial scanning as well. Now, so just to clarify, images can be produced using ultrasound waves. Pulses of ultrasound are sent from a transducer. When the ultrasound wave hits tissues at different density, they are reflected. Now, these reflections occur at different times. Different tissue densities produce different intensity reflections. The transducer detects the reflections which are analysed, and an image is created from the analysis. So in a step-by-step process, ultrasound detectors, such as for fetuses or for shipwrecks, work as following. In the first step, an ultrasound transducer sends out an ultrasound signal. Step 2, when the signal encounters a boundary between two surfaces, e.g. a new tissue or a new object, it will partially reflect. This reflection is then picked up by the transducer, and then using the speed equation, speed equals distance over time, the transducer can build information and thus the image of an object. Now remember, the wave has travelled there and back, so the distance travelled is there and back. So here's an example question. A bat sends out an ultrasonic wave towards a tree. It hits the tree and it partially reflects. The wave takes 2.10 seconds to return. The speed of sound is 334 meters per second. Calculate the distance the tree is from the bat. Well, we use the equation speed equals distance over time. So distance equals speed times time. So the speed is 334. The time to go there and back is 2.10. So you times the two numbers, so you get 701.4 meters. However, the time you've used is there and back. So the distance you've calculated is there and back. So the distance just to the tree is going to be 701.4 divided by 2, which to three significant figures is going to be 350 meters. Now, the use of ultrasound in medical imaging carries no risk to the patient or the practitioner. This makes it the method of choice for antenatal or fetal scanning, as there's no risk to the unborn child since the ultrasound is non-ionizing. It will not cause cancerous growths in the particular fetus or the mother. Now, one problem with ultrasound though is its low resolution. This makes the images difficult to interpret, but is useful for monitoring the rate of development of a fetus and estimating how advanced the pregnancy is. So a scan in the second half of a pregnancy can show any abnormalities in the limbs and vital organs of the fetus. Also, you can use short pulses of ultrasound sent from the transducer, which can travel through the skin to a tissue targeted. Now, the ultrasound waves can cause the particles to vibrate and break up, so it can be used to break down small kidney stones in the urinary tract, making it easy for the patient to pass the stones, or it could be used to break down fat cells or gallstones in the gallbladder. In addition to that, you can have ultrasound waves reflected when they encounter different tissues, which make it ideal to use in physiotherapy as well. Now, we can also use this method regarding waves to make discoveries about the structure of the Earth. Now, in chemistry, you've learned about the different parts of the internal structure of the Earth. So the crust, the mantle, the outer core, and the inner core. So we know with great accuracy the size, the structure, the temperature, and composition of the layers of the inner Earth. So we know all about the crustal, the mantle, the outer core, and the inner core. However, the furthest we ever drilled into the Earth is approximately 12 kilometers into the crust. Now, the furthest we've drilled was actually called the Korora super deep borehole in Russia, and drilling had to actually halt at about 12.3 kilometers as the temperature was so high at this point, the drill bit, which was made of diamond, actually melted. So how do we know about the internal structure of the Earth? Well, we can determine the internal structure of the Earth by using the interaction of seismic waves produced by earthquakes. Now, seismic waves are originated when an earthquake takes place and occur at the epicenter of the earthquake. Now, there are two types of seismic wave produced, the P primary wave and the S secondary wave, and they'll also be referred to as the pressure wave and the shear wave as well. Now, P waves are longitudinal seismic waves. They are produced in the first instance of the earthquake occurring. Now, the P waves travel at different speeds through solids and liquids. Now, S waves, the secondary waves, are produced after the P waves, and they are transverse seismic waves. Now, it's important to note that S waves cannot travel through a liquid. Now, P waves and S waves provide evidence for the structure and the size of the Earth's core. Because S waves cannot travel through the outer core, and because S waves cannot travel through liquids, this tells us that the outer core must be a liquid. Now, this means that there's an S wave shadow on the other side of the Earth to the earthquake due to the liquid outer core. So those S waves will not travel all the way through the Earth to the other surface on the other side of the Earth, because they can't travel through that liquid layer of the outer core. Now, the P waves travel at different speeds in the mantle, inner core, and outer core, which will cause the wave to bend, which it occurs because the materials that make up the Earth must have different densities, and this effect is what we call refraction. So the P waves will refract as they travel through the mantle to to the inner core, and the mantle to the outer core, and the outer core to the inner core, and then the other way around like that, because they're moving from materials of different densities. Now we can also use the time taken for seismic waves to reflect off the different surfaces to determine the depth of the different layers, like we mentioned before with ultrasound signals. Now, the study of seismic waves provided new evidence that led to discoveries by parts of the Earth which were not directly observable. So today we can understand what the solid inner core is like and the liquid outer core is like, and even the mantle, even though we've never actually drilled and seen what they look like, but we've observed them indirectly. So to clarify, seismic waves are produced by earthquakes. The P waves are longitudinal seismic waves, and P waves travel at different speeds through solids and liquids. This allows us to determine the density of different layers of the Earth, while S waves are transverse seismic waves. S waves cannot travel through a liquid, and they allow us to determine that the outer core was a liquid because the S waves do not travel through it. So it's very important to note that the study of the seismic waves provided new evidence that led to discoveries about parts of the Earth which are not directly observable. So to summarise what we've learned in today's lesson, ultrasound waves have a frequency higher than the upper limit of hearing for humans. Ultrasound waves are partially reflected when they meet a boundary between two different media. The time taken for the reflections to reach a detector can be used to determine how far away such a boundary is. This allows ultrasound waves to be used for both medical and industrial imaging. Seismic waves are produced by earthquakes. P waves are longitudinal seismic waves, and they travel at different speeds through solids and liquids. S waves are transverse seismic waves, and they can't travel through a liquid. Now, P waves and S waves provide evidence for the structure and size of the Earth's core. Echo sounding using high frequency sound waves is used to detect objects in deep water and can be used to measure water depth. Then you should be aware that the study of seismic waves provide new evidence that led to discoveries about parts of the Earth which are not directly observable. So if we've been successful and we've learned in today's lesson, you should be able to understand how different sound waves can be used to determine properties of objects. You can calculate the distance an object is away from another object via sound detection, and we can consider the different applications of sound and wave detection. I hope you enjoyed today's lesson on sound detection, which is part of the waves topic in GCSE separate science physics. Thank you very much and have a lovely day.